here.
This meeting's being recorded. Continue.
Yeah.
All right. So if it's showtime, I'm going to wait for this last connecting person. Kalani. Okay. So here we are. It is 4 minutes into the hour, and I've been invited to speak. So I was one of the perps designing USB from the mid 70s on. Now there used to be this thing called Wintel, which was the combination of Microsoft and Intel, and we collaborated with each other a lot driving the PC industry because both of us had a big stake in it. Intel sold most of the silicon and we sold most of the software. So we conspired about these things, hopefully to the benefit of other people. And so I had the great luck to be involved in co-inventing and publicizing USB for 10 years. So I'm going to speak from that experience. So my screen is shared, right? You can see this?
No, you
No.
stop sharing
Not
it.
yet.
Yeah.
Okay, then I will start sharing it now. Okay, good. All right. Here we are. Now you can see my screen, yeah?
Yep.
Good. Okay. So, and I got 12 people on the call. So that's me. You know how to find me. Here's what I want to talk about. I want to give you an overview. I want to talk about what was the problem to solve. Why did we bother with this anyway? Our general solution was to replace physical complexity, all those different connectors and logic, with software complexity and a small number of connectors. So we evolved the physical layer. We developed lots of device specifications for it. And I'll mention some resources and a little bit of my history with USB. So the problem to solve is, so we started having personal computers in the 1970s. Microprocessors go back to 1971. The Altair 8800 came out as a kit in January of 1975. Bill Gates and Paul Allen were expired, and they left Harvard and went off and formed Microsoft. The Altair 8800 used an Intel 8080 microprocessor, which is a 16-bit address, 8-bit data machine that we now would consider comically slow, but it had, 1 megahertz memory bus cycle, and people thought that was a big deal at the time. There were a lot of peripherals to connect to any personal computer. Obvious ones, human interface devices like mice and keyboards. Of course, this was, at that time, Windows was popular, so we wanted mice as well as keyboards. We wanted video to feed to a monitor because the IBM PC had made plain monitors popular. If I went back to the beginning of personal computers, the screens that most people had, well, first of all, there were CRTs. There were no such thing as LCD panels. And so there were all these deep things, with an electron gun at the back, painting pictures on the screen. But the IBM PC made it popular to buy just a monitor with a connector in the back rather than buying a TV set with an antenna, right? We wanted to talk to printers. Why did we want to talk to printers? Because the obvious thing that people did with even the earliest personal computers is word processing. You can type up something, it's only on the screen, you can edit it, and it doesn't waste a lot of paper. And suddenly at the end, you can say, oh, I think I'm going to print that. And you print that, right? So even the very earliest personal computers wanted to talk to printers. And I think I mentioned keyboards already. And then there's communications, like modems. because at that time in history, the only way to get digital data far away was on the dial-up telephone network, which we could repurpose to send bits rather than voice. There was no such thing as the internet as we now conceive of it. I was involved in that, but that's another story for another day. By the early 1990s, 20 years later, things are pretty crazy. So here is a early 1990s personal computer on the back peripheral connectors. So imagine a big chassis about 1.5 feet wide, easy, and it's got a motherboard in it. And the motherboard has a CPU plugged in with maybe some heat sinks on it, and a bunch of memory plugged into it, and a bunch of slots. And each of these slots might connect to something on the outside. And so plugged into these slots, this here is a serial parallel card. So that's a 9-pin RS-232 connector and a spare slot for a printer connector. The old style non-USB printers tended to connect on what they called centronics, and that mapped into a DB25, and that could be plugged in here. Serial ports might also be on a DB25 rather than a DB9, and those were plugs. And so in this particular unit, there were some adapters on the motherboard, and these two connectors were connected directly to the motherboard, and these were extra things plugged in. This here, I believe, was a VGA connector, 15-pin video connection. Here is a 8-pin RJ45 Ethernet, wired Ethernet connector. No, at this time in history, no Wi-Fi, no 802.11. Here is a separate network card adapter with a second DB9 and a separate 15-pin DB connector to talk to an external piece of hardware with coax on it, depending on your archaic kind of Ethernet. Here is another video display, and here is audio card, you know, basically microphone in, speaker out, extra connectors. So we got all this stuff plugged into the back of what is in retrospect a quite heavy legacy PC. And this thing ran, I think I retrofitted it to run Windows for Workgroups 3.11. I might have even retrofitted it to run Windows 95, but it was kind of old by that time. I could afford better stuff. So the problem is this stuff doesn't scale. Each time somebody invented a new kind of peripheral, there was a new connector type. And you could run out of ports or out of bus slots to plug the adapters in. And we sat there at Intel and Microsoft and said, yeah, there's got to be a better way. So we had the idea to start consolidating I/O connectors. So here I'm going to go back and talk about universal serial bus physical layers. Now, how many of you are familiar with the 7-layer communications model? I didn't include that in today's discussion, but the very bottom of that is the physical layer, how you deliver bits, either wired or wirelessly. The next layer up is the media access control layer. And those two layers are abundant in USB and in every other networking technology. So let's talk about USB physical layers. First version of USB, we were targeting HID devices. There was a connector called PS2, right? Something familiar related to PS2 is right here in this recessed connector. So mice, keyboards, trackballs, sketch pads. Not very high bandwidth. Audio, microphones and headphones. So we're feeding in and out, audible sound, but it's getting digitized and delivered at relatively low rates. The public switch telephone network delivers digitized voice at 64 kilobits. And the highest quality stuff that you can hear, CD quality audio, is 44.1 kilohertz sampled 16-bit stereo. That's the very best. If you buy a CD in a store, that's what it, with no compression, that's what it has on it. And so we thought we could get that into USB. We thought we could talk to printers, which normally talked Centronics. And we thought we could do communications. So I had been designing modems throughout the 80s. And so I was hired by Microsoft to be the program manager for modems in Windows. So from that expertise position, I wrote the USB UART specification. So these were things we targeted first. And the data rates were 1.5 megabits per second or 12 megabits per second. And we thought these data rates were fast enough for those first applications. I imagine that most of you didn't exist at that time, right? Is anybody on this call born before 2000?
Yep.
1992.
87.
Okay. So you were around, you antedated this. All right. So that was USB 1. And we started shipping this around 1997, 1998. Started showing up. So there was physical simplicity. 4 wires, 2 power, 2 twisted pair signaling. And the signals are half duplex. That means one device talks and the other one listens at any given time. And that comes out of context. One side is the host. It's in charge. So when a device fires up, the host then goes out and interrogates all the devices and says, who's home? What do you got? What do you do? And for those of you vaguely familiar with it, the A connector is that rectangular thing. And the B connector, the oldest one, is a kind of squarish. If you ever had the 271 lab in our school, the DE1 SoC has a square USB B connector on it. I think mine is downstairs somewhere. Anyway, so the host is supposed to provide DC power, 5 volts. If the host is self-powered or mains powered, it can deliver as much as half an amp. If the host is battery powered, it's limited to delivering 100 milliamps. For some classes of things, that was fine. USB connected mouse, USB connected keyboard, trackpad, 100 milliamps is more than enough. Any questions so far? Hearing none. So the data is encoded, so it's sent baseband. So in the oldest versions of USB, it's going from 0 to approximately 5 volts. Non-return to 0 with bit stuffing means every time you want to transmit a 0, you have a transition on the wire. And every time you want to send a 0, you don't create a transition. And it does bit stuffing. So if the transmitting logic sees 6 ones in a row, that means 6 bit times with no transitions, it will stuff a 0 into the data path, which causes a transition. And the receiver will then look for a 6 ones pattern, and if it sees one and it sees a transition right after that, it'll remove that transition. So it'll insert extra bits and then compact things again. Now each transaction, the host and the device approximately agree on the data rate. So at any given instant, the host thinks it's talking or listening at 1.5 megabits per second or 12 megabits per second. So at that rate, when you generate sufficient transitions using this NRZI thing, you generate lots of transitions. So the receiver can have a phase locked loop. That's what PLL stands for. And that phase lock loop can lock on to all those transitions. So you can regenerate the clock in the receiver. So you don't have to send a pair of wires that says, here's the data, and another pair of wires that says, here's the clock. Does that make sense? For those of you in my class, I'm going to be explaining the same ideas next Tuesday. But that applies to all the synchronous communications. So this is how USB works. A lot of things work in a similar fashion. So here's some physical connectors. I just held up this thing next to the camera. So this is the classic A plug, and here's an A socket. So this cable here is essentially an extender. So here is an A plug going to a micro B device side connector, an A plug going to a classic B connector, an A plug going to a mini B connector. And this is a special case. This is a 5-pin mini B connector, which is shaped differently from this for some reason. I rarely see these in the world. I see these sometimes. I see these. My printer has one of these. These were really, really common and only recently starting to get replaced by USB-C. We'll get there. Any questions about these before I proceed? Hearing none. Okay, so things were evolving quickly in the late 90s. So we said, okay, we got rid of some connectors. Let's get rid of some more. So video is a lot faster than 12 megabits per second. Networks were moving from tens of kilobits per second to Ethernet rates, and Ethernet rates were jumping up to and past 10 megabits per second towards 100 megabits per second, and then gigabit speeds. I'm talking 20 some odd years ago. So the networks are getting faster, and then we rediscovered people had invented flash memory. And people started to think, hey, I could put a flash memory on a USB connector, and now I've got something to replace floppy disks with. Do any of you remember floppy disks?
Oh yeah.
Fortunately, yes.
All three sizes.
I remember the 8s and the 5s and the 3 1/4, 3 1/2s.
They would hold your data for like a week or two, and then you wouldn't be able to read them anymore.
Something like that.
I had my brother and I got a old TRS-80 back in the mid 90s from some relatives, and unfortunately it was old enough by then. When we put the boot floppy in, it ate a nice clear circle in it. So we never actually got to use the thing.
God, I hate that when that happens. Okay, so people had thought of, hey, we want to go faster than 12 megabits per second. If we put flash memory out of there, it would take a long time to empty a flash memory. So what we did is we kept the same 4-wire connectors, and they're still half duplex, but we reduced the differential voltage from 5 volts to more like a volt, and radically increased the differential data rate from 12 megabits per second all the way up factor of 40 to 480 megabits per second, which is about 60 megabytes per second. So that's a big jump. We did that at the end of the 90s. As a side effect, we also increased the DC power that we would deliver to 1 amp if you were self-powered or mains powered. So we can deliver an amp, 5 watts on USB 2. So we did this all more than 20 years ago. Disclaimer. I wrote a patent. It was granted in the middle of 1998, which means it expired almost 6 years ago. But I had that. We're going to get later to how the USB-IF does a good job of defending itself from lawyers, but that's another story for later in the conversation. So we in what some people call the noughties, late noughties, we made a transition to USB 3. This was a longer transition. The previous work had made many connections disappear. You know, DB9s, DB25s, PS2 connectors, all that stuff. We wanted bandwidth enough to cover high data rate video and networking. And the solutions is we went even faster. We have differential signaling over 4 gigabits per second. Now let me ask yourselves a question. Ask yourself a question. So 4 gigabits per second, right? Suppose I'm sending out alternating ones and zeros. What am I producing?
RF.
Yes, you're producing a 2 gigahertz signal that's still pretty big. What signal does Bluetooth work at?
Oh, it's like 2.4 gigahertz, right?
Exactly. So we're putting out something that's almost that fast, which is why it's on twisted pair and shielded. You don't want that waving around. So we went even faster, but to get it to go faster, we doubled the number of wires. Instead of having just power and differential signal, we added a separate set of 2 signal in one direction and 2 signal in the other direction that were each full duplex in one direction. So there's a transmit pair and a receive pair, and then the legacy slower half duplex. So we wound up with 8 wires total. And for those of you who happen to have a USB 3 device, you may or may not be able to see. This is my USB docking station, which I'll talk about later. And you can tell it's USB 3 because they make this blue. Because there's another set of connectors on the other side of that spacer. On legacy Bluetooth, the connectors are all down below. Let's see, I'm trying to work this backwards. So there's connectors down here, right? That's legacy USB, but there's another set up top for USB 3. Make sense? In fact, I want to show you something else. For the devices, for USB 3, you need more connectors. So this is a USB 3 connected terabyte rotating hard drive. And this is the A plug side. And this is the device side. And you probably can't tell, but it's got 8 wires in it instead of 4. And it's shaped differently. So it fits in here, right? Just a little show and tell. So that's part of the transition to USB 3.0. So we now have something that's fast enough for video, even 4K video. So I happen to own a pair of adapters. One of them is a USB 3 to VGA adapter. And I have in one of my drawers a USB 3 to HDMI adapter. And I need those because this 8-year-old notebook, those connections failed for some reason. So if I want to drive HDMI from this legacy notebook, I need that adapter. And I have one driving VGA for my second screen, which you'll see here, right? So here's my main screen, here's my spare screen, and my printer over here. So far, so good, right? So that's going to 3.0. Now, what are we going to do next? Well, how many of you have ever paid attention to USB-C before other than having it as a product?
I tried to a little bit. Doesn't it have the pins mirrored and also allow for higher power levels?
Yes, you've done a nice job of it. So my last mobile phone, which is now what, 2 or 3 years old, has a Samsung S10 has a USB-C on it instead of a micro B connector. So first thing it does is it leverages USB 3 PHY layers, so it runs faster. And it's double mirrored, so it's got a row of connectors on one side and a row of connectors on the other side, and you can rotate it 180 degrees and it'll still work. Which means that, I mean, people are used to fumbling with, here is a micro B, right? Powering my Bluetooth headset. And you always have to look to see, does it go in this way? No, it goes in this way. People got kind of tired of that. And so they designed USB-C to be convenient. And they were successful. So it's got a new connector and it has USB power management. It's also bidirectional. It's designed so that any device in principle can be the host or the device. Like if I plug this thing into my PC doesn't know any better, so it thinks that it's in charge. So it treats this as the device. So it owns bus transactions. But in principle, this can be a USB-C host, and we could design things that plug into this as peripherals. They already make USB-C memory cards that you can plug in here. And this thing will say, oh, a memory card, and start dumping all of its files to that memory, right? That happens all the time. And some of these new and interesting devices, like if you're familiar with an analog discovery module, some of you have used them in classes.
Oh yeah, they're nice.
Right. Now, in principle, they've already got waveforms running on Mac OS. They've already got waveforms running natively on Windows, of course, and they already have it running on PC-based PC-based Linux distributions. So Android is another Linux distribution called Android. So impossible to port waveforms to this mobile phone and to have a simple adapter that goes USB-C to USB-A and drives an analog discovery module. I would buy one right away because I think analog discovery modules are really handy. And so that's a lot of the things that are going on with USB-C. It is, you can rotate it and either device can be the host or the device. It's versatile that way, but then there's power management. So we're looking, and my successors are looking at USB and thinking, how many connectors do I have on this gadget? And they started thinking not only about replacing video connections, and USB-C is fast enough for the video connections, but with, depending on what your device has, it can power a monitor if it runs on 100 watts or less. It can power a notebook if it runs on 100 watts or less. So in legacy USB before C, the host could discover and interrogate all the attached devices. And one of the things it would do is it'd say, how much current do you want? And it would provide that current if it was available, and it would send a message that says, I don't have this. If it's a battery powered system, not self-powered, and it doesn't have enough to deliver, it'll say so. But in USB-C, there is one wire that's used simply for power queries and replies. And USB-C defaults to 5 volts, which is what legacy USB does. But it also has optional voltages of 9, 15, and 20 volts. So there are options to provide up to 5 amps if the cable can handle it. Let me mention something that's not in a slide, but it's true. The chips that can capture and respond to USB-C signaling can be made as something small enough to bundle into a cable, if that's all it does. And so if you want to deliver 100 watts to something, you have to buy a cable that has one of these chips in it. And all that chip does is respond to the query messages. You can have a host that can deliver 100 watts and a device that wants 100 watts, but the cable has to agree. Cable has to say, oh yes, my cable is fat enough to handle what you want to do. Because if it's, the older USB cables weren't heavy enough to handle that much, 5 amps. But the new one cable, if it's can say, yes, I can do that, the host can say, yeah, you can have 5 amps. Do you follow what I'm saying? So when if you are going in the future trying to connect things together and you want to deliver power over USB-C, make sure that you buy a cable that's smart enough to handle that query. Otherwise, it won't work. All right, so keep going. Let's talk about devices and managing these devices. Now, I've simplified this a lot, so hopefully I still remember the answers to your questions. One of the tasks that I had at Microsoft and then later at MCCI was I was in charge of the networking device working group. And we covered Ethernet connected things and mobile phone connected things. So USB has host and device roles. Now, traditionally, the host has that rectangular A port and the device side has some smaller port. And I already went through showing you what some of those look like. The host begins connectivity by finding, I missed a B, a D here, finding and interrogating each USB device. So all the devices, they might come up and they'll come up waiting for the host to interrogate them in turn, in which case it's their job to respond to what the host asks them. And this process also works through USB hubs, if you know what USB hubs are. To give you an example, I'm going to turn off screen sharing for a second. And I'm going to, that makes my camera larger. So to deal with all the connectivity on my PC, I have a powered USB hub. So it gets USB 3 from the PC, and then it drives the printer, it drives the camera, it drives my headset, it drives a charging port, it drives the mouse, it drives the charger to my smartwatch, and it drives an adapter to drive VGA for this monitor. So I've gotten rid of that big collection of slots in that 1990 personal computer, and I've replaced it with this powered USB 3 hub. That makes sense? I'm going to share that screen again. I just thought that would be amusing digression. So the host shepherds each device through several steps. First of all, it's powered. That means that device manager or its equivalent in macOS can detect it. Then it starts interrogating it. And as part of its interrogation, it will decide what its address is. So a device doesn't power up with an address. It gets interrogated and told what its address is. Imagine for a moment that I was the host of this meeting and all of you just showed up, and I would choose one of you. I want to ask you a bunch of questions, and I'd say, your name is Ethan Ma. And I might interrogate you and ask you a bunch of questions, and I'd say, your name is Yuki Rivera, right? Or whatever name I made up was. That's what happens in USB. So the host learns capabilities, and one of the things it does after it learns its capabilities is it loads a device driver to match the device, assuming it's got one. How many of you know anything about operating systems to know what a device driver is?
Yep.
Right. Good. To live in our electronics engineering world, you need to know what device drivers are. So all communications is packetized. The host will send packets to each device it finds. Each packet is sent by host includes what address it's being sent to, some ID for the packet, like keeping track of them all. So if you're doing anything but isochronous, you number these things, and the sender expects an acknowledgement back from the receiver that it got it. Each packet will contain what are called TLV formatted messages. TLV means it's got 1 or 2 bytes that say what kind of message it is, 1 or 2 bytes that say how long the message is, and indeterminate number of bytes to be the message that's being sent or sent. As you study other communications methods, you'll find repeated uses of TLV formatting. It's everywhere in USB. It's everywhere in Wi-Fi. It's everywhere in Bluetooth, etc. How many of you ever heard of CRCs before? CRC means cyclic redundancy check.
Oh yeah, that's a great error to get.
Well, you don't want to get the error, but what happens is the hardware watches all the data goes by, and it composes a CRC attached, which it attaches to the packet. So when the receiver computes its own CRC and looks to see that it matches the CRC that the transmitter sent, if they match, it's happy. It'll probably acknowledge the packet and then do something useful with the results. Whereas if the CRC that's transmitted doesn't match the CRC that's computed by the receiver will probably say, I don't like that data. Send it to me again. Success requires each address device to reply accurately in turn. Okay. So configuring pathways. So there are logical pathways over all these physical wires. And the one level is called an interface, and interfaces can have one or more endpoints. So how many of you have ever launched Device Manager in your personal computer before?
Yes.
Right. So when you launch Device Manager, I don't know if we have time for a distraction because it's already 8:15, but if I launched Device Manager and connected my TI Tiva to USB in Device Manager, it would show up as a Stellaris drivers twice, because one's the control channel and one's the device firmware upgrade channel. So it would show up as a multi-interface device. And if I lit up my computer, I'm sorry, my printer is several times the mass of my notebook, but it's a, it's a 4-color laser printer with a scanner and all these other features, right? So it looks like a whole slew of interfaces to my PC. Now, so like I say, a multifunction device may have several interfaces. My Tiva has 2. My printer has more like 6 of them. Each interface has 1 or more endpoints. Each endpoint can be a control endpoint that's high priority, but usually pretty small. It can be a bulk endpoint, which is expected to be error corrected. If you send a bulk chunk of data in a CRC and the receiver doesn't like it, you'll send it again until it's believed. An interrupt packet, those are time dependent and have high priority. If a device needs some attention, it'll send an interrupt packet, for example. They can be isochronous. So if I'm streaming audio, it'll be an isochronous endpoint rather than a bulk endpoint. If the data is bad, you throw it away and you keep receiving. You can't go back and say, oh, I didn't like that, because you don't have time. Any questions about endpoints before I proceed? Hearing none. Okay. So this is a list of the kinds of things that a host will ask out of a device. It'll first of all say, and this is a 4-character number. No, I say a 2-character number, 4 hex digits. Give me the spec release number that you were designed to, so that the host knows how to accommodate that device. It'll say, what's your device class, which is a single byte. There's a lot of standard device classes defined by USB. And if it gets an FF, it means that this is manufacturer specific. It's possible to use a standard interface like USB and do new things. And this is the flag that says I'm doing something new. It'll have another byte that says, here's my subclass. Like there was a class for networking devices, and we had at least half a dozen subclasses. We might also have a byte that identifies what the protocol is, especially if there's a diversity in protocols. An important number is the max packet size. How big a packet might it send to you? How big a packet can it handle before it chokes? Separately, I'll have information that says a 2-byte code that says who's the vendor, a 2-byte code that says what's the product reference to this vendor, and then I will have a 4 hex character number that identifies the release number of this device. Further on down, I have indexes into strings. If I have found, let's say inside my PC, a device driver for this thing, the INF file as part of that driver will have some long strings. So we don't expect the device itself to produce these long strings, but the device driver will be able to tell you here, spelling it out in English characters or in Chinese characters or whatever characters, the manufacturer, the name of the product, and the serial number for this thing. So you can keep track of what it is that you're calling tech support about. The last number is how many different configurations does this thing support? Because the device manager is going to want to know that. Any questions about these things? I include this here because I'm trying to give you a sense about the complexity involved behind the scenes in what we at Microsoft used to call plug and play. You know, people like to be able to buy stuff, plug it in, and it just works. But this is a piece of all the stuff that happens rapidly and is hidden to make it all seamless.
So, what's the difference between the product and the product index of a string?
Well, this here, product here, this is probably a 2-character number. I'm sorry, a 16-bit number. In fact, the vendor ID and the product ID will probably be used by the host operating system to locate the correct INF file. Whereas you don't expect a human to read this 16-bit or 16-bit number. You don't expect a human to read this 16-bit number. But the same thing says, here's the index. Use these to find the INF file in the driver. And then these indexes then tell you what character strings that are readable by humans. You know, this could say Microsoft. It could say J5 create. It could say the name of anything. It could be almost arbitrarily long. And this could say the name of the thing, however long it is, in human readable form. Serial number is probably a string of Arabic digits. Even the Chinese use those. So does that answer your question?
Yeah, that
Good.
makes sense.
All right. So traffic patterns. I simplified a lot of this stuff. USB 1 runs a bus cycle of 1 kilohertz. That means the host will initiate a series of transactions at a 1 kilohertz rate. The host initiates at that rate. The host will undertake a series of bus transactions in each cycle. You know, it will assign high priority to its own control traffic, then priority to interrupts, receiving interrupt cycles from anything that needs attention. Then it will allocate some space for isochronous stuff, and any spare bandwidth it's got will be applied to bulk. And USB 2, it's 40 times faster, but it runs those bus cycles at 8 kilohertz instead of 1 kilohertz. So the maximum packet size under USB 2 is still 5 times greater than the maximum packet size here.
So what does bus cycle actually mean? Is that like, so 8,000 times a second, it's going to look for new devices or something?
Well, it could do that too. Usually it sees transitions that,
Is this like a similar thing how operating systems can switch contacts between processes, that this
no.
switches devices? No?
I think that's a leap too far. But imagine any given USB set of wires. So there's a host and it connects to a bunch of devices, right? So I'm going to turn off my camera again and point, I'm sorry, my screen sharing again and point this camera at this USB hub, right? So here is a USB 3 wire or set of wires going into this powered USB 3 hub. So it at least 8 kilohertz rate, the control channels, you know, there's the duplex wires that run at USB 2 speeds, and then the full duplex stuff runs at the 4 gigabit per second speeds. But the control stuff is still on that wire. So it will, at 8 kilohertz rate, go out and interrogate everybody, deliver traffic to and from endpoints that have been previously booked and configured. So if it's got nothing to say to the printer, it won't say anything to the printer, so the printer will stay asleep. It's busy using streaming video data from the camera. So that's isochronous traffic coming from the camera. Here it's talking to my headset. It's doing audio in and audio out. That's slow enough to easily fit in USB 2. And it's sampling it and outputting it probably at a 64 kilobits per second rate. Here it's talking to a mouse, this little mouse here, and this little mouse may or may not be running at 1.5 megabits per second, because mice don't need to do any more than that. And here it's talking to my smartwatch charger. And if it's ever going to do a firmware download, it might run probably USB 12 megabit per second, because that's probably fast enough to download new firmware into my smartwatch. Here, it's going to a VGA adapter, and so it's probably using the extra 2 pairs, sending data at very high rates to make sure it's got plenty of bandwidth to cover VGA video. That, and it does bus cycles at probably at that rate. Did I answer your question?
Probably, but I didn't quite get it all. But it's okay. It's okay.
All right. So I'm going to go back to screen sharing again and finish up. So I'm back screen sharing, correct? You can see the traffic patterns?
Yeah.
Yeah.
Good. Okay. So legacy audio device classes. One of the things that Microsoft did, I'm getting a little bit ahead of myself, is they put device drivers built in to Windows starting with the introduction of USB. So a lot of the makers of these devices didn't have to make their own printer drivers anymore. Microsoft was responsible for designing them and testing them. So we did audio drivers, we did smart card drivers. This is an international specification for smart cards. We bundled UART communications and modem communications into it. So I was responsible for managing a component called Unimodem. And Unimodem had support for USB connected modems. And that means that US Robotics and all those other companies could get out of the modem driver development business, as long as they met our specs. Content security means if you are selling very expensive software, you might want to have a hardware key that this very expensive software goes out and says, oh, you've got your hardware key. You can run my code. Otherwise, I won't run. HID devices, human interface devices like mice and keyboards. IRDA, which means infrared data. Okay, so common TV sets and HD, you know, media players and whatnot, a lot of them that have infrared connected remote controllers, they all use this spec here. And so there is a USB spec so that you can attach a USB connected infrared transmitter or receiver to USB. So mass storage, obviously these things have taken over. Printers, all those Centronics printers went away and they all went to USB. We had imaging like cameras. So I have a digital still camera and it's got it has a micro USB B connector on it, right? Nobody makes proprietary camera connectors anymore. So those are a lot of legacy device classes. Any questions about before I go forward to why it has, in my opinion, been a successful spec? First element is that we were the dominant player in personal computers. We were working with Intel to make the user experience better and make plug and play a reality. So half of that bargain was to put device drivers for all those classes of devices in Windows. So for those people, all they had to do was plug it in and it would work. So we incorporated that into Windows OS, and so they would got that benefit. The USB Implementers Forum has had regular international testing events for at least 25 years. And so the builders of new devices are encouraged to attend and test their devices against a variety of corresponding hardware and software. And proof of interoperability is required to gain access to the USB compatible logos, which are outside the boxes, right? But there's a nice flip side to that as well. Every company, and there are tens of thousands of companies that are part of the USB Implementers Forum, are required to pool any patents they have. So if you want to build a USB connected device, you got two choices. You join USB-IF and you prove compatibility, in which case you get access to the logo. You can put it on your box, and you're protected from all the lawyers connected to all those patents. Or you can ship it without being part of the USB-IF, in which case you're bait for lawyers. And I'd much rather not be bait for lawyers, right? We successfully made USB relatively safe from patent trolls. Side note, so 20 years earlier, I'm working on the design for Atari's serial I/O bus, which shipped in 1979. It predated USB by 18 years. A patent troll came along at the end of the last century and tried to sue USB for infringing on their patents for a serial bus. And we said, hey, were you aware of this thing here for which Atari didn't file any patents? But that's public art 18 years before USB was published. And that means those patent trolls had to go home empty-handed. I was glad for that. So that collection of things helped make it a success. Now, my own personal computer history, we're getting close to the end. Right. So here's where I was with a desktop PC in the early 90s with all these connectors. This is repeating a slide you've seen earlier. All right. 20 some odd, no, 15 years later, I have a notebook and it has a power connector. It has an optical drive that'll take CDs. It has 3 USB 2.0 connectors. It's actually sitting here behind me. This notebook here, fat ass notebook, it's got VGA, HDMI, it has RJ45 for Ethernet. It also has an RJ11 for a dial-up modem, back from the days when people still had dial-up modems, and has 1, 2, 3 USB 2 connectors on it. I don't know if you can see that because it's all black, so there's no contrast, but you got the basic idea. So it has that, plus it has one of these little secure digital MMC slots on it. Here, I don't know if there's enough contrast for you to see it, but that's where my thumb is. And it has 2 3.5 millimeter jacks for microphone in and speaker out. Okay, so that's halfway through this period. Here's my notebook in front of me. It's 8 years old. It's got a power connector. It's got an optical drive for CDs and I think DVDs. It has 3 USB 3 connectors. Those are the faster ones. It has VGA and HDMI, both of which are broken. It has an Ethernet port on it, but it no longer has a modem port on it. It has an SD slot on the front, and it has an earphone jack for audio out, but it doesn't have a jack for a microphone in. So here's my 5-year-old MacBook Air, and it has power, 1 USB 3 slot, 3.5 millimeter microphone out. It's got an SD slot on it, and it's got a second USB 3 slot, and it has a lightning connector. And the lightning connector, you can hook up extra video outs on it. So that's a 5-year-old design. Now, I bought myself a new notebook 3 weeks ago. Microsoft Surface 4. It has power. It has a single USB 3 slot, a single USB-C slot, and a 3.5 millimeter earphone jack. That's all. It only has 4 connectors. Now with that, I have bought myself a docking station. And so I can plug this in. Where is it? Here we are. I can plug this in. Got it upside down. So I plug that docking station in, and it has, I am sharing also, right? So you can see in the shared screen, I can plug VGA into it, HDMI into it, Ethernet into it, a couple of USB 3 extensions, and I can plug in something that powers it so it can be a powered hub. So that's the evolution of connections for me. I've got my newest machine has only 4 total connectors on it. And the only legacy connection is the 3.5 millimeter earphone jack. So let me close up with some resources. Here are a series of websites. Here's the main USB website. Here's the 2.0 spec, the 3.2 spec, the USB-C spec, and their document library, which is where all the device class specifications are, for one. For two, I've got a series of now dated books which explain pretty well in a lot of detail how to design a device to work with USB. And that's me and some machines I worked on and what my email addresses are, etc. So, any other questions, ladies and gentlemen?
I apologize. Could you go 2 slides back to the one where it was the list of books? Yes, this one.
Okay, hang on a second.
So these will actually explain in full detail how to design a device to talk to USB.
I don't think he can hear us right now. But it seems to be the case.
I should probably, there is an alias I think I have for the student branch, and I should send the PDF of it to all of you so you don't have to take notes. So here's one of those books. Here is a book by my buddy at Intel. And here is yet a third book on the subject. So you sort of know what they look like. Now, all of these were second editions. There may be third or fourth editions by this time. So,
are you on Discord, Joe?
I have a Discord account, but I basically don't use it.
Oh, all right. Do you want to upload? If you upload the file to the chat, we can post it.
Okay. Here's what I'm going to do. I'm going to escape. I'm going to let's do a save as. No, that's the wrong place to put it. Yeah, here we go. Let's make a PDF out of it. There we are. And that means now I want to, well, let's find it here. All right, so let's see. I'm going to stop share. I'm going to go into chat. I can actually, wow, look, I can send, I didn't know I could send files.
Oh, wow. I didn't know either. Huh.
Your computer. Well, what the hell? Desktop.
Is it not working there?
Well, no, I'm hunting through my file system and finding, here we are. Boom, open. It's 1.2 megabytes. Done. So I just sent it to chat, of all places.
That is actually the first time I've seen a file transferred through Zoom.
Yeah.
I haven't tried that before. I didn't know that was possible, and I've been on Zoom for a year.
I think they added that recently.
Well, there we are. Learn something new every day, I suppose. All right. So, anything else I can do for you, ladies and gentlemen, today? Because we've gone over time.
Going back to bus cycles for a second, clarifying question. So it's like a single bus cycle would be like a single transaction of data.
Well,
but with
it's not a bus cycle in the same way that you put out an address on a bus and you send or receive data on the data bus as one action. Bus cycle is more like on a 1 kilohertz or an 8 kilohertz basis, you start a bus cycle. And in that cycle, the host controls what happens during that cycle, during that series of bits. So let's suppose it's USB 2 and it's 480 megabits per second, right? So if you divide 8 kilohertz into 480 megabits per second, you're talking about a very large number of bits that are transacted in each cycle. So there's a whole lot of packets that are going to be sent and received in that cycle. Remember, USB 2, for example, is a half duplex bus. So all transactions will begin with a message from the host that says either, I'm going to send you this thing, and then here it is, please acknowledge. Or it's going to be a message that says, I'm expecting this transaction from you. Respond by sending me the packet that represents what I'm just asking for. In which case the host will then send back a packet that says, yeah, I got it. And so there'll be a whole series of transactions that occur in that 125 microsecond time period. And then another bus cycle will start and it'll repeat again. Does that help you?
Yeah. So the amount of data that it transfers in a single bus cycle, would that be dependent on the data rate of the device,
Well, the
is it?
upper bound is 480 megabits divided by 8,000, right? So you were talking about 60 million bits per bus cycle total.
Okay.
And that gets divided down in all kinds of ways.
What I was asking was, is it a fixed amount of data per cycle, or is it a fixed amount of time per cycle?
Fixed amount of time.
Got it. So
and the amount of time will be determined by mostly by the host, because the host has interrogated all the devices and found out which interfaces are active and which endpoints are active within each interface, and been configured about how often those things need attention. And so for each bus cycle, the host will then run around and say to this device, here's some data, and to this device, I want some data, and to this other device, we're going to trade some data, and so on, based on the way that they'd been configured. It's a much more flexible thing than in a traditional CPU architecture, where there's one device in charge, the CPU. It puts out an encoded address to some device or some IO device that says either I want you to give me your data or I want to give you some data on a cycle by cycle basis. This works differently. And it's a lot fewer wires, but running screaming fast. I mean, seriously, if you look at your own, I look at my own PC in front of me, right? and it's a 1.6 gigahertz, 64-bit wide, 4-core i7, right? And so its external bus is probably SD-RAM, where it's probably doing synchronous transfer at least 1.6 gigahertz times probably 128 bits wide. But that's mostly dealing with, recovering from cache hits. I'm sorry if what I'm saying doesn't quite make sense, but modern machines are extraordinarily complicated. So their idea of a bus cycle is a little bit different from a USB bus cycle. But we use the same word to describe them.
Thank you so much.
All right. We're supposedly, if you've got the time, up in a week to talk about Bluetooth.
Yeah. So next week we'll have Joe again, and he'll be talking about the wireless networking.
Well, Bluetooth, I thought I was going to focus on Bluetooth. But if you want, it's a little bit broader topic to talk about wireless networking in general, because there's at least 3 major technologies to consider. Bluetooth at the shortest ranges, mobile networking all the way up through 5G is the longest range, and Wi-Fi and 802.11 are in between.
We could probably just stick with Bluetooth if.
Okay.
Yeah, because I imagine that's quite a bit of information as well. So.
Right. Yeah. Well, it probably won't fit into an hour either. All right. So I think we're done, and I think I'm actually off for the day. I started on Zoom today at 11 o'clock, and I'm kind of done.
Yeah.
Thanks,
So
Joe. We appreciate
I'm
it.
gonna stop recording here.